Okay, relatively quick proof here. We have a quadrilateral, and we're told that the diagonals bisect each other. So that means that diagonal BD cuts AC in half, and that diagonal AC cuts DB in half, right? Which means that E to B, E to D, E to C, E to A, they're the same. Well, not all the same, I guess, but this side's the same as that side. So, okay. And we're asked about the side lengths. Well, it turns out the opposite sides, these two sides, AB and DC, are going to be the same length, and that AD and BC are going to be the same length. We're going to prove that. And again, we're going to basically go about the same procedure we have been going through, which is to find a couple of congruent triangles and use those congruent triangles to conclude that certain parts of the triangles, namely these two sides, are congruent. So we're going to start out with AE and EC being congruent, and DE being congruent to EB. And that's just given to us. That was the information that we started with. Next, we've got that angle AEB is congruent to angle DEC. And our reason for knowing that is that these are what are called vertical angles. Anytime two lines cross, the angles that are formed kind of on opposite sides, there's a name for them. They're called vertical angles, and they're the same measure. By the way, these over here would also be considered vertical angles, and they would be the same measure. Now, again, not all four sides aren't the same, but just the one. Not all four angles are the same, but just the ones that are across from each other are the same. So AEB, DEC are the same, and on the other side, BEC and AED, those are the same. Which tells us that these two triangles here, AEB and CED, that they are congruent because they have two sides and an included angle being congruent. So that's side congruent to side, angle congruent to angle, and side congruent to side. So we have triangle AEB being congruent to, and be careful here. Notice how we went down the side that I marked. So I marked them as being congruent in the diagram to help us remember. But AEB, so down the 2-tick side and up the 1-tick side, so we have to go the same direction with the other side. It has to be CED. Now, the corresponding parts will match up in the names the same way they do in the diagram. Okay, and then that tells us that AB must be congruent to DC by corresponding parts of congruent triangles are congruent. And then finally, we know that AB is equal to DC. So see how I took the little line across the top. Now, when I have a little line on the top, I'm naming the segment by name, and we're saying that they are congruent. And here, we're saying that the definition of being congruent is that they're the same length. So AB with no line over top refers to the distance from A to B. And DC with no line over top refers to the distance from D to C. And so we're saying that, well, we've determined that they're congruent because corresponding parts of congruent triangles are congruent. And what does it mean to be congruent? It means that they're the same length, that these two distances are the same. And this last line isn't super necessary for the proof. We could have just stopped at saying they're congruent, but I want to toss it in as a reminder that those are two slightly different things, two slightly different statements. They're congruent is one thing, they have the same length as another. And both things sort of imply each other. If I know one, I know the other's true, but they are slightly different statements. Because again, AB with a line over top is the name of the segment. Right? That's like saying your name is Bill or Joe or Harry or Sue or whatever. And AB with no line over top is a number. It refers to the length of the segment. Like say your height, I'm 5'10", I'm 5'8", 6'2", whatever. right? It's something about the segment, right? And they can sometimes get confused because a segment doesn't have a whole lot of properties. There's not a whole lot of things to say about a segment other than its length. So, but they are two different things. And so we've just proved that if the diagonals of a quadrilateral bisect each other, then opposite sides are congruent, or the same length. Now we could turn the proof the other way and do the same thing for these two other sides over here, but that's not really necessary. I guess I think we can do without saying that extra bit. But we could prove that BC and AD are the same length using the exact same argument and just have to use these two triangles instead. And there you go.